energetically charged particles being thrown off, while these are like actual waves.
Waves. Yes. Yes, and waves have particle behavior, like it's weird. Get into Einstein's theory, wave-particle duality. But yes, there's no mass to them. They come in, they have wave properties that you can predict based on wave formula and mathematical correlations. They also have some particulate properties as well. So you can say like a wave of light, right, can be packaged as a photon of light that is a discrete unit or particle nature, but it moves like a wave. I know. Me too. It's all very strange, right? When you get down to the micro field, the tiny. All right, but this is our electromagnetic spectrum. It's all based on the size of those waves coming in, right? So the smaller that you get, right, we can classify it into two major different categories based on the frequency of the wavelength. And so these two are called ionizing radiation and non-ionizing radiation. So ionizing radiation, so what is an ionization energy? What do we already define that as? The ionization energy. The amount of energy it takes to take one what? Electron. To pull an electron off an atom. That's the ionization energy. So we talked about that already. That is ionizing radiation as well. Ionizing radiation will pop electrons off of atoms, right? So it has enough energy that it can overcome the ionization energy of things that it hits, right? And everything is made up of atoms. So if it's hitting DNA, it's going to pop electrons off the DNA molecule and damage it. If it hits protein, if it hits other tissues, it's damaging that tissue by pulling electrons off of it. So that's ionizing radiation. And the forms that do that are gamma rays, X-rays, and some ultraviolet. So like UVC can be very damaging. UVB as well. So if you're out in the sunlight and you get a bad sunburn, right, it's the ultraviolet rays of the sunlight that are causing the damage to your cells, right? So that burn, right, is actually ions coming off of your skin molecules. Poor skin. All right, non-ionizing radiation is not strong enough to pull electrons off, right? So you don't get ions forming in that case, right? So that's going to be our visible wavelengths, the infrared, the microwaves, and the radio waves. That doesn't mean that those aren't maybe dangerous. You wouldn't want to put yourself in the microwave, right? Right, so our microwaves, we're concentrating those microwaves. They have a lot of heat energy associated with them. Heat can be damaging to our systems as well. It's not going to ionize our bodies, but it would cook them, denature them, and be bad for us in general if you have concentrated microwaves. All right. Okay, so that is electromagnetic radiation. Right, we have the ionizing radiation, again, some UV, X-rays, and gamma rays. The ones that have very small wavelengths, they again carry enough energy to pull electrons off the atoms that they hit or move through. Okay, and our non-ionizing, again, the radio waves, microwaves, infrared waves, and the visible spectrum, and some of the ultraviolet radiation. Okay. So these usually do not cause as much damage as the ionizing radiation. But if they're concentrated, they could based on the heat that they can cause. Okay. Back to gamma radiation. All right, so if an atom is decaying and releasing that gamma ray, again, the M in this case is used to indicate the higher energy state of the unstable parent nuclide. And then that is gone in the daughter nuclide, so it's now more stable, and it's released that gamma energy. Okay, so of the 3 radioactive decay pathways that we've talked about thus far, the gamma rays are the most damaging, right? They are just a wavelength and they can penetrate quite far into the body. The electron is a particle, and so it will go in pretty far, but it's going to hit something and stop. And the alpha particle is quite big. The neutrons and the protons are quite big, and it doesn't typically pass the skin. Like your skin will block an alpha particle. So gamma rays are the worst, like if you're going to have radiation. So sometimes in radioactive decay, you can have multiple forms of radiation coming off at the same time. So this happens with radon, right? So radon will decay into polonium, which is going to release an alpha particle. And during that transition, it also releases a gamma ray, right? So it's got kind of both of those things, right? And so for this one, again, the mass is going to change. So I've gone from 222. My daughter nuclide is now 218, and we're emitting that helium nucleus. The proton number also has to change because 2 protons came out. So I've dropped from 86 to 84. And so we could predict based on where we are in the periodic table, 86 is radon, go back to 84, there's polonium, right? So we can determine what our daughter nuclide would be based on the periodic table and the proton number. So proton number determines the element that you have. And then there's also a gamma ray that pops off. How do you know when you have a gamma ray wanting to pop off? I'm going to have to tell you, right? Like you don't have to memorize that or know, oh, this one will decay and form a gamma ray. I would tell you, oh, I might give you like radon and say radon decays by releasing an alpha particle and a gamma ray. What is the resulting daughter nuclide of that reaction? And draw that reaction. Right, so from that information, you should be like, oh, gamma ray, I know what that is, 0 and 0. I know an alpha particle, right, is going to decay into a helium atom, a nucleus, and you can put that on there too. All right. Okay, so far we've talked about the alpha particles, the beta particles, and the gamma rays. These are the most common radioactive materials you'll see coming off of a nucleus of an atom. Right? The alpha particle, again, is the helium nucleus, mass unit of 4, 2 protons. A beta particle is an electron coming out of the nucleus. A neutron is going to change into a proton during that process. And then the gamma rays, no mass, no charge. The parent nuclide doesn't really change, but it releases energy and becomes more stable. All right, so again, penetrating power for alpha particles, it's minimal. It will not penetrate the skin. Beta particles have more short penetration, and some tissues might get damaged. And then the gamma rays are the worst. You'll have deep penetration there, and tissues will be more damaged when you have gamma radiation. All right. So alpha, beta, and gamma. All right. Whoop. All right, so here's another diagram of the strength of our radiation. Again, the alpha particle, because it's so large, right, it's going to get blocked. It'll get blocked by paper. It'll get blocked by your skin as well. It won't go through. Beta particles can be blocked by aluminum, but it'll go through paper. And then gamma particles even go through lead, right? So they're very reactive when they're coming through. And again, because there's no particle associated with them, they're harder to block and harder to stop. Okay. All right, so we have a couple other types of radiation that can come out of the nucleus. So these include positron emission, which is a beta plus decay, and electron capture. So The positron emission, I think, is equally as weird as the beta decay, saying an electron is going to come out of the nucleus. So in positron emission, there is the emission of a positron from the nucleus, and we haven't even talked about these particles, but they are positively charged particles that have the same mass as an electron. The only difference really is that they're positively charged, right? So essentially, I've got my notation here for that particle coming off is still an E, because it's the size of an electron, but the charge is positive instead of negative. So if I have a positive thing coming out of the nucleus, in this case then, I'm going to change the positive thing in the nucleus, right, the proton, into a neutron. So it's kind of going in the opposite direction. So here, if we're looking at oxygen, right, and we're emitting a positron from it, right, this is oxygen 15. The mass doesn't change because that particle really doesn't have any mass. So my nitrogen here is 15. But I've changed a proton into a neutron, and so I've lost a proton in this case. The positive charge comes out of one of the protons, and now it's neutrally charged, or its charge is balanced now. So you have to, 7 plus 1 has to equal the 8 over here. 0 plus 15 equals that mass. So we can check on our periodic table again and say, oh, 7 protons, that's now a nitrogen atom when you have positron emission or positive beta decay. So weird things, protons can change into neutrons by emitting a positive particle. Neutrons can change into protons by emitting a negatively charged particle and becoming positive. The world's a strange place. It's radioactive decay. All right. Okay, so our positron is essentially the opposite of an electron. Positive particle that has a very, very small mass associated with it, the same as the electron. Okay, and our positive charge, without the loss of any mass, causes the conversion of a proton into a neutron. All right, so our mass doesn't change, but the number of protons does change, and so the identity of the daughter nuclide is going to be different. All right, so our final radioactive is electron capture. So if the nucleus captures an electron, right, that electron is going to combine with a proton and become a neutron. Like, what? Why? But that is what is happening here. So on the left side of the equation, right, I've got my parent nuclide. It is capturing an electron. That electron is going into the nucleus in this case. It's going to interact with the proton in there and neutralize it so that the charge is balanced now. So you're shifting a proton into a neutron. So I have to take away a proton and push it up into the mass. It's still in the mass because it's a neutron. And there's no emission of a particle in this electron capture. But I've changed my parent into a daughter because I changed the proton number. Okay. So the electron combines with the proton, converting it into a neutron in electron capture. So mass number stays the same, only the proton number changes because the proton and the neutron have the same mass. All right, that is the complete weirdness of our radioactive particles. So this is a great table. It's a summary table of all those different radioactivities. You've got the alpha decay, right? And so it's showing you up at the top here, the nuclear equation, essentially. The arrow should be right here. I don't know what happened to my arrows. They're kind of missing. The electron capture, right, is going to be, the arrow should be there and the plus should be there. Okay, so you've got your equations. You've got a summary here. The atomic mass decreases by 4 with alpha decay. Your Z number is your proton number, is going to decrease by 2. For beta decay, the atomic mass is unchanged. Your atomic number increases by 1. For gamma decay, both are unchanged because you're just emitting a wave. For positron emission, the atomic mass again is unchanged, but your Z number decreases because you're converting a proton into a neutron. And same with electron capture. Your atomic mass is unchanged, but you're also converting a proton into a neutron. You will have this chart for your exam. So you can use this chart to help you build equations or confirm things for beta decay, alpha decay, all of that. Let's take a 5-minute break and then we'll do some Socrative practice. This is a lot of lecture. I also, if you haven't picked up for the online portion, the stuff you need for lab this week, I also have kits for next week's lab as well if you want to pick those up now. Only the online section. The A is atomic mass, the Z is your atomic number of protons. Yeah. Take it. Do you want me to write it? No. All right. Yes, that's why I want the pennies.
I could give, but I was like,
Cool, thank you. You bet. Awesome. You need a kit. Sure, that's for week 3. Have you finished week 3? No. Okay, keep that for week 2. And let me know your
Cynthia.
Ah, wait, perfect. Awesome. Okay. Week 3, you already have 2. Yeah, there's an online section on the lab, so I can have you make I do. Oh, yeah. So this is what you'll need. Send me an email after class and I can tell you that.
Okay, and then it's just
Yeah. Your name?
Helen.
And you were in the afternoon lab, remember?
And then basically when I do this, it's just basically. And then I will write like someone did
Yes. Yeah. So if all the instructions are on there, there's like a ventilation area and then.
Thank you so much.
You bet.